let's dive into what we have for today. So we continue on real analysis. So the first thing we have here is equivalence classes. So let's quickly talk about that. Now, equivalence classes. Now, when two sets are said to be equivalent, what we are trying to say is that there is one-to-one mapping between sets. Maybe set A and B. This instance now, there is a one-to-one mapping between set A and set B. And to explain this, let's just take an example now. Let's take an example where we have set A to be 1, 2, 3, and our set B to be A, B, C in this instance. So we can say A is a one-to-one mapping with B if the function that relates A to B, take for example, we have function, the element of A gives us a unique element in B. That is, take for example, for this example, we can have our function for when our function is 1, or when the variable is 1, it gives us A in B. It gives us the element in B. And then for when the function is 2, we have f of 2, it gives us B. And we have when f of 3, we have C. This actually explains that they must have the same number of elements. That is the only situation where we can have the equivalence class. So what do we mean? What we are meaning is that if we have 5 elements in A, for it to be equivalent to B, B must also have 5 elements, and it must be mapped in such a way there's a unique element in B attached to each element in A by the function. So let's continue. So let's move into the next thing we are looking at for today, which is countable and uncountable sets. This is also very important. We need to differentiate what countable and uncountable sets are. So for a countable set, now a countable set is a set that is finite. Let me say a finite set. A countable set is a finite set. So a set is said to be countable if either the set is finite or it is a set of natural numbers. Now, natural numbers subscript n. Now, when a set is a set of natural numbers, it means it is countably what? Countably infinite. That is, what we are trying to say is we have set 1, 2, 3, 4, 5, 6 up until you continue like that infinitely, because the set of natural numbers are infinite. So an example of countably infinite sets, like I've said, is subscript n, a set of natural numbers, set of integers and rational numbers. So we have natural numbers, integers, and rational numbers to be examples of countable sets. So let's look at the next thing we have, which is uncountable sets. Now, a set can be considered uncountable if it is not countable, that is, if it is not finite. A set that starts from infinity, negative infinity to positive infinity is an example of an uncountable set. It's an example of an uncountable set. So an example is our set of rational, so our set of real numbers. Set of real numbers R, subscript R, and the set of complex number, subscript C. Now we need to understand that when we have two countable sets, when you add them together, it also gives you a set that is also countable. And also a subset of a countable set is also countable. So the mother gives birth to the child, not the child giving birth to the mother. But as a result of the mother giving birth to the child, it means the child is from the mother. So if the set is countable, the subset will also be countable. So let's move on. Now let's talk about the real number system. Now the real number system is very, very important, and for our introduction we will have to explain to start in a way to make you understand the importance of the real number system. Now remember that the rational number subscript Q is as presumed to be the largest set because it contains a set of natural numbers, it contains integers. So we assume it to be yes. It's the largest. It's one of the largest sets because it contains other infinite sets. But when we come into higher level mathematics, we observe that some certain things do not hold the rational numbers. Take for an example, the solution. There is no solution for an equation x squared is equal to 2, because this gives us x is equal to 2. So there is no definite rational number m over n that is equal to 2. And now this takes us to proving whether there is no rational number or there is a rational number. So we need to assume that there is a rational number for this solution. And remember that our rational numbers now, if we want to prove our rational numbers is defined as a set of m over n, where m comma n is in where n comma n is in the set of integers, So m over n represents a rational number in a situation where n is not 0, which will make the fraction undefined. So as long as n is not 0, it's a rational number. So we need to take our rational number to be p, or any letters. Then we now express it as pq, p squared is equal to 2. So since a rational number is p, now remember it is defined as a set of numbers m over n. So we can replace our p here, which is a rational number, with m over n. So when we do this, we substitute it into p. Then we now have a result m squared over n squared equals to 2. And then from this we simplify further. You notice we have m squared is equals to 2n squared. When you cross multiply, you have m squared is equals to 2n squared. But we need to observe that from this solution our m is even. Why? Because there is an even solution in our right hand side for m, because we have 2n squared. So if n is even in this instance, and remember that in irrational numbers we are having m over n such that m over n there is no common factor. That means if our m is even, our n must be odd. So we need to check whether our n is odd. So but to do this, we need to observe that since we conclude that m is even, that means m itself must be a multiplication of 2 and a certain number, which represents an integer as k. So m now will be 2k. Represent our m as 2k. So we put this 2k to represent n in our equation. So when we square it, we have 4k squared equals to be 2n squared. So we make n squared the subject of the formula, we perceive that when we make n squared the subject, it becomes 2k squared, because 4 divided by 2 gives us 2. So this also means that our n is also an even number, because it is having an even solution in the right hand side, 2k squared. And remember that rational numbers q, subscript q, is defined as a set of numbers m over n. M over n. They don't have any common factor. Remember, but here we perceive and we have seen that m and n has common factors because they are both even, so they have common factor of 2. So this means that there is no solution for this expression in the rational numbers, because the rational number has to be in its simplest form m over n, such that m and n have no common factor. But in this instance, there's a common factor. This does not make it a rational number, because it contradicts the rule for rational numbers. So this does not hold for rational numbers. Then we have proven that there is no solution for x squared or b squared is equal to 2. So we've successfully proven that. So next we'll be going into properties, actions, because this brings up the development of the new real number systems, from which we go into the actions and properties of a field. Now, to develop this new number system, which we call the real number system, the major focus of deriving this real number system is to accommodate numbers like root 2, root 3, root 4, sorts. Numbers like sorts. You know what sorts are. So this real number system we will be able to accommodate. And then to develop this real number system, like I said, we will need some actions. these actions will propagate. It will develop the real number systems and its properties, which will accommodate those given numbers. So let's look at actions and properties of a field. Now a field can be represented as F. So now let our F be a set containing elements, that is, contains more than one element, like A, B. And there are two functions. Remember the Cartesian product, F cross F. Now what is this trying to tell us? That it is mapped onto what? Onto itself. That is, when we talk about reflexive functions, we talk about reflexive fields. So we have a Cartesian product of F cross F. So the element in F is what? Is related, when we bring in relations to it, is related to the elements in F, which is a reflexive form. So there are two functions, F cross F into F, which is the addition and multiplication group denoted by what? Our plus and our multiplication, which is dot. That means for our action 1, which is our very first action, we'll be having commutativity, where we have A plus B is equal to B plus A. For where A plus B is also in our field, since A and B is in our field. So for action 2, we have A plus B in bracket plus C is equal to A plus in bracket B plus C for all A, B, C that is in our field. Now we go to our next action, action 3. Now this tells us for all, for all vectors, that is for all elements in our field, not vectors this time around, there exists a zero vector. That is when we add a zero vector with a zero element with our E. It gives us E. It returns our elements. Action 4 also adds the negative element. So for where there's A in F, there's a negative also in F. For when we add it to it, gives us 0. For 5 to be have A dot B is equal to B dot A. And we also have our action 6. So there are basically 9 of them, with which I'm going to list above, writing it down. So all we need is actions and properties to guide us with the real number system. We have our action 7, which is an identity action, and that is telling us that there's an identity element in the field, such that when you multiply that element with another given element, it returns that element. For 8, we have an inverse of an element, such that we multiply A dot the inverse of A, it gives us 1. And then for 9, we have addition of our elements multiplied by another element. So it's distributive, it gives you AC plus BC. So next, in our next chapter, we'll look at the properties of a field. So that's where we stop today.